Space, the final freeway. These are the voyages of the car ship Effortless.
Captain's log, Science Officer Spark reporting. Car date 3.14159265.
Just say Tuesday, Mr. Spark.
Captain, I failed to understand.
It's okay to round off. Really.
Captain James T. Circuit in command. We have been ordered to this quadrant to restore the operation of a signal vessel damaged by an ion storm. The USS Effortless is now lying close to the damaged vessel, preparing to effect repairs.
Greetings, Mr. Spark.
Very low power emanations from the ship, Captain. Records show the XL model to be a sophisticated design, late 20th century Earth.
Mr. Scope, prepare to transport to beam over.
Aye, Captain. We have a wee bit of a problem with the modulation crystals. If you could stand by for just a second, we'll have it fixed in a jiffy.
My instruments indicate an electrical problem on this vehicle.
The sparks? A spark?
Perhaps, Captain. These vessels have many electrical devices. However, electrical terminology and methods of that period differed substantially from ours.
I wish I had taken the refresher course at the Academy. How was I to know that electrical theory would be important to me?
May I remind you, Captain, that it's called electricity because of the action of electrons. Every atom in the universe has electrons or the capacity to attract electrons. Hence, electrical energy is a universal force.
I bow to your fundamental knowledge, your ability to troubleshoot systems. Can your photographic memory help us here, Spark?
If you'll permit me, Captain, I'll use a telepathic mind link to remind you of some basic electrical principles.
By all means.
I'll present this information as it would have been presented to a student of that era. The term electricity refers to the movement of electrons in a conductor. You realize that all matter is made up of molecules which are themselves made up of billions of atoms. It is the relationship of protons, neutrons, and electrons in each atom that helps determine how that atom will combine into molecules. Energy can knock electrons loose from an atom and set them drifting until another atom gathers them in. Usually, because they're spread out evenly, they'll drift randomly, making little jumps in all directions, from one atom to another. But if there are too many electrons in one place and too few in another, the drifting electrons will flow toward the shortage. When all this movement is in one direction, it makes a noticeable current, like the current of a river, and its flow will continue until the electrons have spread themselves out evenly again.
And that flow of electrons is called current.
The general name for the flow of free electrons from atom to atom is electricity. The more specific name for the direction and pattern of the flow is current.
Electricity flows in a current. Yes, I remember something about that.
If the current flows easily through a material, that material is called a conductor. Because of their structure, most metals are good conductors. Our scanners show us that copper, aluminum, and steel are conductors in this vessel. Anything that inhibits the flow is called a resistance.
Maybe the problem here is too much resistance.
Not necessarily, Captain. Resistance to current flow isn't always a malfunction. An electrical component like a light bulb, for example, presents just enough resistance for current flow to work for us. In this case, heating the filament and creating light. All materials resist electricity to a certain extent. Some just a little, some resist it a lot. Materials with a resistance so high that it prevents electron flow completely are referred to as insulators, such as plastic, rubber, insulators around wires. By understanding these characteristics, we can channel and control the electron flow to do work and perform many helpful tasks.
What causes current to flow in the first place?
Permit me, Captain. With the aid of the ship's computer, I'll demonstrate. If you'll recall, I said that left to themselves, electrons tend to balance equally with protons throughout a material. Extra protons give the material a positive charge. Extra electrons cause a negative charge. When protons and electrons are even, the charge is neutral. Since it takes energy to draw electrons away from their atoms and hold them together in one place, a difference in charge is really stored energy. When you have a positive and a negative charge close together, the scales, in effect, are tipped. That tipping of the scales is called an electrical potential, because what you have is a potential, a possibility for current to flow. Given this chance, the current will flow through the conductor until the scales are balanced again.
But without a potential, no current.
Correct, Captain. Practically speaking, if you want current, you must create a difference of charge, a potential, and then bridge it with a conductor. Would you like a moment to consider that, Captain?
I would, Spark. 20th century thought takes some getting used to. Let's continue, Mr. Spark. How do you create a difference in charge, a potential?
The energy to create a potential can come from many sources. For example, it can be generated by heat, by pressure, by magnetism, or by chemical action. This vehicle uses a combination of chemical and magnetic sources to create an electrical potential, which is measured in volts, and it's called voltage. A good analogy would be two water tanks connected together, one tank containing more water than the other. Voltage in this analogy would be the water pressure created by the difference in level between the two tanks, and the energy it took to raise this water to the higher level. This energy will be released as the water pours through the pipe, attempting to equalize the level in each tank. We call this flow current. The resistance would be the size of the pipe, or perhaps some valves we introduce.
So, all electrical circuits have at least three factors: voltage, current, and resistance. Spark, it seems to me that as the voltage goes up, the current would go up. But as the resistance goes up, the current would go down.
Excellent, Jim. You've just stated Ohm's law.
I was going to call it Cirque's prime directive.
Actually, Mr. Ohm discovered it first. It is the prime directive of electricity. It's one of the simplest and most useful electrical laws. Observe it on my viewing screen. Ohm's law states that current is directly affected by voltage, and it is inversely affected by resistance. Ohm's law is the basis for electrical troubleshooting. First of all, each factor, voltage, current, and resistance, has its own unit of measurement. You already know that for voltage, the unit of measurement is volts. For current, it's amperes, or amps. And for resistance, it's ohms. The following symbols represent our three factors when the law is written. E stands for the electrical potential, which we know is measured in volts. I is the intensity of the current, which we measure in amperes or amps. And R is the letter used to represent resistance, which appropriately enough is measured in ohms. Now we can easily see the remarkable relationship between voltage, current, and resistance. Ohm's law can be stated in several ways. E equals IR, R equals E over I equals E over R. Let's look at a circuit with 6 amps of current and a resistance of 2 ohms. Using Ohm's law, we can tell that the potential in the circuit must be 12 volts. Let's assume that we're now trying to find the resistance. In a circuit with an electrical potential of 4 volts and a current intensity of 2 amps, the resistance must also be 2 ohms. Now let's change the resistance and see what the new current will be. If the resistance increases to 4 ohms and the voltage remains 2 volts, The current intensity must now be 0.5 amps.
And when there is no more potential, no voltage, or the resistance becomes infinitely high, like with a good insulator, there is no more current. Well, it's really quite simple, isn't it?
Very good, Captain. And now it's time to beam to the damaged vessel.
Prepare to transport, Mr. Scope. Energize, Mr. Scope.
Fascinating.
Spark, the Cochrane warp drive, I understand, but this... I don't recognize any of these devices. Such massive components.
A basic form of power, Captain, but very advanced for its day. Fossil fuels were mixed with oxygen and ignited in the cylinders by a sequence of electrical sparks. The resulting explosions drove the pistons and imparted motion to the crankshaft.
How does Ohm's law help us here, Spark?
Well, at the moment, we're standing on a 12-volt battery. Actually, you'll find about 13 volts in a fully charged battery, but it's rated at 12 volts. A potential, that is a difference in charge, of about 12 volts has been generated and stored in 6 cells in this insulated plastic box. As long as that potential exists, we can cause current to flow through this system.
Is the current flowing now?
No.
Well, why not? We have a battery here for electron potential, conductors to carry the current. Ah, I know, Spark. It's been 200 years. Maybe this battery is finally empty.
Possibly, Captain. Though its energy is supposed to be replenished by the engine during operation.
So how do we check this? How do we measure the potential, the voltage?
Your communicator, Captain. Mr. Scope, beam down the equipment, please.
Equipment, Spark?
Compliments of Mr. Scope. From his personal collection, an analog VOM, volt ohmmeter. One advantage to simpler technology, simpler tools. Set the meter to the proper scale. One moment, Jim. With these analog devices, you should always set the range slightly higher than the measurement you expect, so as not to damage the meter by overloading it. If you set it too high, you can always reset to a lower scale. Now, touch the probes to the terminals on the battery. Be careful of your polarity.
Polarity? What's that?
This is a direct current circuit. One side is always positive, one side is always negative. As a result, the current always flows in the same direction. Some direct current devices become damaged if the current flows through the wrong way. That meter is one such device. It has markings for the positive and the negative poles. When you connect to the circuit, you must respect the polarity or the meter will be destroyed.
Plus to plus, minus to minus.
That is correct, Captain. You've now created a circuit. The electricity from the battery is doing work. It's deflecting the needle in the meter as it moves through the conductors and the coil of the meter. The potential energy we talked about earlier has been converted to a different kind of energy. We call it kinetic energy. And it's a type of energy that does work. It moves things and heats things.
Is that why light bulbs get hot?
Indeed, Captain. Heat is a form of kinetic energy, and it is the most common way that electrical energy is released. The components in all circuits release heat, like a light bulb as they operate. And unless one exercises care, the heat can become intense enough to damage the components.
I'm not getting 12 volts here.
Yes, Captain, the reading is a bit low. One of the cells may be dry. Indeed, the cap of this one seems to be dislodged, perhaps during the ion storm. Shine your flashlight down here, Captain. The electrolyte is low.
What is the electrolyte?
A liquid found in this cell. This is a rechargeable lead-acid battery. It converts electrical energy into chemical energy as it charges, and chemical energy into electrical energy as it discharges. In order to charge and discharge properly, a reaction needs to take place between those lead plates below us and the electrolyte solution, which is ordinarily found in this chamber. It consists of a solution of sulfuric acid in water. It was necessary to add water at regular intervals to the earlier type of battery because it tended to evaporate over time. The concentration of acid would be fairly high when the battery was charged.
I don't understand something. If there is no electrolyte, no acid solution, this cell can't function. Why did my volt-ohm-meter show voltage in the battery?
Apparently only this cell is low, Captain. While the output of this battery is below normal, it might be adequate for our purposes. Our major problem lies elsewhere. Our battery is functioning, and our time grows short. I suggest we replace the cap and press on.
Captain's log, car date 4:59:69. Thanks to Mr. Spark, my electrical knowledge is increasing rapidly. But the malfunction in this Hyundai still eludes us.
Captain, our efforts to this point have shown us the difficulty is not in the battery. Perhaps there is a short circuit elsewhere in the system.
Short?
Here is a simple circuit drawn schematically. We have a source of electrical potential, in this case a battery. We have a resistance, in this diagram a light bulb. We have a conductor. Here it's a wire. And we have a switch to make and break the circuit. When it's functioning properly, the electric current follows the designed path, heats the filament in the light bulb, and does the desired work.
Spark, in the diagram you're showing me, the current is flowing from positive to negative. If electrons always move from negative to positive, isn't that diagram backwards?
Another interesting vestige of 20th century thought. Humans of that era couldn't decide which way best described the movement of the current. Hence, in the literature of the day, you might find it described either way. The electronic theory had the current moving with the electron drift from negative to positive. But the more common theory described the current as moving from positive to negative. For a long time, this was the convention, so it has been known ever since as the conventional theory.
Which is correct?
It's a human description, Jim, of a complex natural phenomenon. You will find both descriptions used in the literature, and either description could fit the facts. Are you describing the electrons moving to the right, or the holes their absence creates moving to the left? Perhaps we should leave the philosophical implications for another time.
I agree. You were about to describe a short circuit.
Yes, Captain. Here again we see our normal circuit.
Looks like the conventional theory of current flow.
Correct. The current flows along the designated path from positive to negative. But if the current finds an easier path, a path of less resistance, it will be drawn away from the circuit and wasted. In this illustration, opening the switch won't stop the flow of current through this part of the circuit, because a difference in potential will continue to exist between the positive terminal and the ground until our battery is completely drained.
The ground? Spark, we're in space. There's no ground within 200 million miles.
It's a traditional term, Captain. You see, what matters in a circuit is the relative difference in voltage between one part of the circuit and another. Often it's convenient to have one standard of reference, a zero potential, in relation to which all other voltages are either positive or negative. This standard potential is called the ground.
So I don't have to connect the circuit to the dirt.
No, indeed. In this case, the ground is the chassis of the craft. So if this circuit were shorted to ground, it would have nothing to do with actual soil.
Aha. Perhaps you haven't noticed, Spark. This circuit is grounded.
Yes, Captain. The circuit is grounded. But it is not shorted to ground. By connecting the chassis to the negative terminal with this wire, we assure that both are at zero potential. Now, any common reference points in our circuit that need to be connected to ground, to zero potential, can be connected to the chassis, and it will be the same as connecting to the negative terminal. This saves a great deal of wiring, and it keeps our schematics from being hopelessly cluttered, because whenever we need a common connection to zero potential, ground, all we have to do is draw this symbol and connect to the chassis ground. If the circuit made electrical contact with the chassis at some point where it shouldn't, then it would be shorted to ground, and our current would be wasted.
But we know the circuit in this craft hasn't shorted, because if it had, there'd be current flowing, or no voltage in the battery. It would have been all drawn away.
Excellent deduction, Captain.
Now, you said this battery stores energy and converts it from electrical to chemical and back again. It doesn't generate energy?
No, it's a storage battery. One moment, Captain. Let me record some of this data.
Mr. Scope, beam us to our next position.
Here, Captain, is the alternator. The source of energy that's used to charge the storage battery when the engine is operating. The motion of the crankshaft is transmitted here by means of this belt. It turns the rotor of this device which produces electrical energy, using the principle of magnetic induction.
That principle has slipped away from me temporarily.
If I may, Captain. The principle of induction can be easily explained. Magnetism is one of the elemental forces that act on matter. When a conductor is passed through a magnetic field, the moving lines of magnetic force impart energy to the atoms in the conductor. They force current to flow in the wire. This device is constructed so that magnets and their fields rotate constantly within these coils of wire, thus producing a steady flow of current.
Spark, correct me if I'm wrong. As the magnet rotates, the magnetic fields pass the wire coils in alternating directions.
Correct.
So the current must alternate too. It must flow back and forth through the wire, following the movement of the magnetic fields.
Superb analysis, Jim. That is precisely what this device produces, alternating current. That's why it's also called an alternator.
But you said these vehicles use direct current.
It does.
So what's the gadget that converts alternating back and forth current to direct, continuous current?
It's called a rectifier. It comes in many forms, but the type best for our purpose is made with diodes. A diode is a device that allows current to pass in only one direction. It's only a conductor part of the time. Only when the current enters from the proper side. Because of this, it's called a semiconductor. This is obviously another of those devices where polarity is very important.
Does this belt connect the alternator to the engine?
Yes, it does, Jim.
And the engine goes faster and slower?
That is absolutely correct.
So, if with the change in speeds from faster to slower, the amount of voltage produced will vary considerably.
That is absolutely correct, Captain.
So, turning the alternator at faster or slower speeds will cause the amount of voltage produced to vary considerably.
That is correct, Captain. So there is another component, a voltage regulator which prevents the voltage from becoming so great that it causes damage to the circuit. It also controls how much of the output is used by the vehicle and how much is routed to the battery to recharge it. The higher the RPMs, the more excess energy is available for charging.
Maybe the voltage regulator on this machine has failed.
That might account for the weak battery. However, the alternator is intact.
Boy, I wonder how they managed to do anything without dilithium.
Yes, Captain. Technological advancements in the late atomic age were not terribly consistent with intellectual processes.
Well, I disagree, Spark. The design of this craft is both logical and consistent. We know now that the chemical energy from the fuel has been converted in the cylinders to mechanical energy, and that rotates the alternator, which converts the mechanical energy to electrical energy. And the rectifier, with its diodes, changes that alternating current to direct current. And the voltage regulator then stabilizes and controls the electricity as it's distributed to various parts of the craft. For example, some of the electricity goes to the sparks.
The ignition system.
Oh, very well. And the excess is used to charge the battery, which then stores the energy once again as chemical energy. When the engine is idling or stopped, as it is here, the alternator can't meet all the demands of the electrical system, so the current once again comes from the battery as it discharges.
That is absolutely correct, Captain.
So what starts the whole thing going?
A starter motor cranked by the battery. It uses the principle of magnetic induction in reverse, drawing electricity from the battery to create magnetic fields, which turns the motor.
It must take a lot of energy to crank this enormous engine.
Yes, Captain. The starter motor draws many amps. It's actually the highest current drawing device on this craft.
Well, we now know that voltage is the electrical potential or pressure, and current represents electron flow and movement, and resistance slows down or stops current flow. Now, Ohm's law states that as the resistance goes up, the current goes down. And as the voltage goes up, the current goes up. We can use a volt-ohm meter to measure the potential or the resistance. And I would imagine there's something called an amp meter to measure current.
An ammeter, Captain. Your analysis is perfect.
So why doesn't this circuit work?
I took the precaution of copying the shop manual onto my tricorder before we left. Here's the wiring diagram for the entire electrical circuit.
I recognize some of these symbols from the diagrams you showed me earlier. This symbol is the battery. These little symbols are the chassis grounds. And these light bulb symbols, the taillights.
Correct, Captain.
What if one of them is out? Wouldn't that break the circuit?
No, up until now we've been looking at circuits where everything is hooked together in a line on one wire. It's called a series circuit. Break it anywhere and the current stops. But the taillights in this circuit are wired in parallel. The taillights aren't hooked one behind the other in series. They're wired in such a way that the current divides to pass through each of them at the same time. This is a parallel circuit. If one of them goes out, the current can still complete the circuit through the other branch. Most large electrical systems combine both of these circuit types, series and parallel, together, because each is appropriate for particular tasks. For instance, on this craft, the dash and instrument panel illumination circuit is a series parallel circuit. We have another stop to make, Captain.
You're right, Spark. Beam us to the next position, Mr. Scope.
This is an important stop, Captain. The fuse box.
What's this, Spark?
Another of Mr. Scope's vintage tools, a test light, Captain. Gives quick indication of whether voltage is available at various points in the circuit. These fuses, for instance.
What do they do?
One moment, Captain, I'll demonstrate. If you'll recall, Captain, I mentioned earlier that all parts in a circuit generate heat when current passes through them. The more current, the more heat. Of course, there's a limit to how much current the circuit can handle. These fuses are a limiting device. When the current exceeds safe levels, the material in the fuses heats and melts, breaking the flow of current, before more important components can overheat and be damaged.
They look all right.
Looks can be deceiving. First, let me ground the test light.
I see. The ground completes the test light circuit.
That's correct, Captain. This circuit is switched on. Touch the test light to that exposed spot on the left side of the fuse. And this one.
There's no light on either one, Spark.
As I suspected, Captain. Here's where we should have begun. These fuses blew out in the ion storm.
Can we replace them?
That would seem to be in order. Finished, Captain.
Current is flowing, Mr. Spark.
Job well done, Captain.
Circ effortless. Mr. Scope, are we signaling?
Aye, Captain. 'Tis a glorious sight.
Very well. Mission accomplished. Beam us on home. And we finished our engine inspection and completed our repairs by replacing the headlight and taillight fuses and refilling the battery with electrolyte. Did you get all that, Mr. Chekhov?
Yes, Captain.
Send that off to Carfleet. Well done. An important navigational beacon has been restored with the help of a little old-fashioned electrical know-how and a spark of genius.